Here we're going to look at a MOSFET being used in a switch as a circuit. And again, in this course we focus on an enhancement mode N-channel MOSFET. You should also know how the P-channel works, and we discussed that the only difference between the operation or how you operate a P-channel and an N-channel is you just flip the polarity of the voltage sources. So let's go ahead and look at the two most common type of MOSFET switch circuits. Now, no matter what type of MOSFET switch circuit you have, one condition is that, or the condition actually, is that Vin of your circuit, which is connected to the gate of the MOSFET, and Vin is just equal to VGS. Well, that Vin can only be one of two values. One of the values of VGS will make the channel open, and the other value will ideally make the channel a short. So, most typically your VGS value to make it open just be 0 volts. Okay, as we discussed earlier with an enhancement mode MOSFET, if the gate voltage is 0, then you don't have a channel, and essentially it's acting like a switch that's open, a switch that's off. And then the other value of input voltage, which again is the same as VGS, is much larger than the threshold voltage, meaning that the channel will act like a short. So, this is how you get it to act like a switch, is just you use the two extreme values of VGS, one that makes it an open and the other that makes it a short. So here's one way that we could control some device like a motor or solenoid, or say a lighting device like an LED with a MOSFET switch. You can see the input voltage tied right to the gate like I mentioned previously, and then here the drain is connected to a resistor to that device out to some source voltage V. So let's look at both cases of Vn. Let's start with when Vn is equal to 0 volts. Well, when Vn is equal to 0 volts, you're going to have an open from drain to source. That's where your channel lies. Remember, the channel is between the drain and the source of the MOSFET. Okay, so if Vn is equal to 0, meaning your gate to source voltage is 0, there is no channel, and you've got an open between the drain and the source here. So that means your device current, okay, that I'll just label ID, okay, I device, okay, which equals the drain current, which is the same thing as the channel current here. Well, that's just going to be 0 since there's an open. Right? Since there's an open from drain to source, you don't have a complete path for this source for current to flow, since the current for the source can't get back to ground because of this open here. So here, clearly the device would not operate, so the device would be off here. Okay, no current flowing through, so if it's a motor, it's not going to spin. If it's a solenoid, it's not going to be energized. If it's an LED, it's not going to light. Alright, now let's say Vn is the other value. And as I mentioned in a previous video, let's say your threshold voltage is a volt. Typically threshold voltages are around a volt or so. Well, a VGS of 5 volts would be considered much greater than. Okay, so let's say Vn is now 5 volts. And since this value is much greater than the threshold voltage, well, now the drain to source is essentially going to act like a short, ideally. Okay, in actuality, there's a few ohms there, but we're just going to consider it a short. Well, if there's a short from drain to source, you now have this circuit here. You just have a short between drain and source, right, where this side is ground. And then you got this resistor, RD. That's RD. Right, this is the device. I'll just abbreviate DEV. And then here's plus V. So you see now the current that flows, okay, which again is your device current, which is the same as your drain current, which is the channel current. Well, say your device is a motor or a solenoid, you would just use the resistance of that device and treat it like another resistor. So your current is just going to be the source amount plus V divided by just the two resistances in series. okay, RD plus R of the device. Okay, now if the device was an LED, well then, just like in LED problems that we've done previously in the course, now your current, right, your device current, which again is the same as your drain current and your channel current, well now it would be V minus whatever the drop, the forward bias voltage drop across the LED is. You know, if it was a red LED, we'd use 1.5, and then that would be divided by the drain resistance. Okay, so how you treat the device, whether as a resistance or as a voltage source drop, just depends on what device you have. In this class, if it's anything but an LED, you treat it just as a resistor, but if it's an LED or a diode, say a diode that doesn't give off light, you would just treat it as a source of voltage drop equal to the forward bias amount of voltage. Now there's another way that you can connect the device up to a MOSFET switch, and that's here. Okay, you know, the previous circuit had the device in series with the drain resistance. This circuit has the device essentially in parallel with the drain and the source of the MOSFET. So here, let's see what happens now for the two values of Vin. So let's again start with Vin equal to 0 volts. Okay, when Vin's equal to 0 volts, the drain to source is open. Okay, how the device is connected up in the circuit doesn't affect when the drain to source is open and when it's a short, right? Because that's a product of how the MOSFET is fabricated. Well, you see, if this isn't open from drain to source, in this case, with the device connected as you see here, there is a path for current to flow through the device, right? Because none of it's going to go to ground through the drain to source because there's an open. However, it can get to ground through the device. So you see here, when your input voltage is 0 and the drain to source is acting like an open, that's when current's going to flow, and your I device, okay, which would not be equal to the channel current in this case, right? Because see, the channel current's here, which would be 0. So you see this here, the channel current would be 0. Okay, but you do have device current, and that device current, just like before, would either be V divided by the total resistance, or if you had an LED, it would just be V minus VFB over RD. Alright, so you see here with this configuration, when Vn is equal to 0, it's the same as when we had, as far as the device is concerned, it's the same as when we had Vn equal to 5 volts for the other configuration. Now when Vn is equal to 5 volts for this switch circuit, well, the drain to source is going to be a short, just like it always is when your VGS is much greater than the threshold. But you see, the circuit you have now looks like this. You have a short from drain to source that goes to ground like that. Then here's your device. Oops. And then you have RD, there's your plus V, there's RD. Okay, so now look at the path of current. The current's going to flow here, and when it gets here, ideally all of it goes through the short between the drain and source to ground. None of it goes through the device. So here's where the device would not operate, right? Because there's no current, so your device, you know, would be off. So whether the device operates or not when you have a MOSFET switch circuit depends on the configuration. If the device is configured like this, it operates when Vn is equal to 0, and it doesn't operate when Vn is equal to 5 volts. With this type of configuration, well, it operates when Vn is equal to 5 volts, and it doesn't operate when Vn is equal to 0 volts. Now, which one of these two switch circuits would you want to use? Well, it just depends on your particular application. In some applications, you want this to occur. In other applications, you want this to occur. So it's just application. The application decides which one of these two switch circuits you would end up using.